So here I'm going to explain our circuit from lab 8, which as a whole is a voltage controlled oscillator, VCO. But first we'll talk about our circuit from part A, which is set up on this part of the breadboard. This is our constant current source. So what it does is that it takes in a constant voltage, and given the voltage that you're feeding into the sub-circuit, you can control this constant current that it outputs to the rest of the circuit. And you are allowed to alter that voltage based on the potentiometer that's built into the constant current source sub-circuit. So here we have our graph of our input current to the sub-circuit versus its output current. And we see a very linear relationship, which we should expect because of Ohm's law, which is a linear relationship between current and voltage given a resistance. So when we fit our slope, our line with the trend line, we get this slope of 972, which corresponds to the load resistance that we've given to our sub-circuit, which is given by this 1 kilo ohm plus or minus with 5% tolerance resistor, which fits very well with our linear slope. So next is our second sub-circuit for the VCO, which is the Schmitt trigger, and is set up on this portion of the breadboard. So what the Schmitt trigger does is that it is fed in some kind of voltage, and then depending on two threshold voltages that the Schmitt trigger is designed with, it outputs either a high output or a low output, meaning that those are the two states for the Schmitt trigger. So why it's useful is because it acts like a comparator in that it allows you to know whether you're at low or high voltages given these reference voltages that you designed for it. But since the Schmitt trigger also has hysteresis, unlike a comparator, it can deal with slowly rising and falling signals. And now finally we talk about the whole VCO, which is also, in addition to the current source and the Schmitt trigger that we talked about before, also has an inverter built in and this current mirror sub-circuit. So what the VCO as a whole does is that it allows you to feed in some constant DC voltage to the whole thing, to the whole VCO, and then give this oscillating output depending on the states of the current mirror and all the other sub-circuits that work, effectively changing a DC signal into an AC signal, given which the two voltages that will come out from the AC signal correspond to the real voltages that are given by the design of the VCO. So here we have the output for the VCO, and we see that, first of all, biggest thing is that normally when we have this rising slope, so we're at low voltages going to high, we would have a low output. However, since this is an inverting Schmitt trigger built into the VCO, we have flipped voltages, so we have a high output state as you're going from low to high voltages, such as in this part where the troughs and peaks of this waveform correspond to the rail voltages, to the threshold voltages that the VCO is designed with of 3 and 7 volts. So as we go from low to high voltages, you get this high output, which since it's an inverting Schmitt trigger, we know that we must be at below our high threshold voltage at that point. As you descend from 7 to 3 volts, so you're decreasing, you get this low output, so we know we must be decreasing from our high threshold to our low threshold.